Assalamualaikum. Today we are going to discuss how basically elements are identified using their group numbers or period numbers or rows. So if we are to start up with, let's say this represents a certain sketch of the periodic table. Group 1, then this becomes group 2, then these represents the transition elements, then the remaining families 3, 4, 5, 6, 7 up till 8. So let's say this is group 3, group 4, group 5, 3, 4, 5, 6, and 7, and this is finally let's say 8. So group 1, group 2, group 3, then let's say this is group 4, 5, 6, 7, and 8. So it is very easy to understand this periodic table. Basically, how is that so? Because every element in the groups, let's say we are considering lithium, sodium, potassium, rubidium, cesium, and francium here. So whatever elements are placed in group 1, they have one valence electron. And to understand what is the concept of one valence electron, you need to focus and you need to scroll through the previous videos. I can repeat this as simply one valence electron basically means the last shell of an atom has only one electron. So all these elements, lithium, sodium, potassium, rubidium, cesium, and francium, they have one valence electron. That means they have only one electron in their last shell or outermost orbit. Now, if they want to become stable, so rule of stability was divided basically accordingly into two categories. Either it can be a duplet rule or it can be an octet rule. So if we are working with duplet rule, this rule is valid for hydrogen, helium, and lithium. However, for the remaining elements, octet rule is valid. So if we are considering that any of these elements that belongs to group 1A wants to become stable, so how would they would be longing for stability? Let's consider this lithium. Lithium has an atomic number of 3. That means its K shell has 2 electrons and L shell has 1 electron. So as you can see this very clearly, this is the last shell, and since this lithium was belonging to group 1A, it has 1 valence electron. Now if lithium wants to become stable, what it can do is it can basically lose this electron so that it goes back to the duplet configuration, which is a stable configuration. Let's consider sodium. Sodium has an atomic number of 11. K shell would have 2 electrons, L shell would have 8 electrons, M shell would have 1 electron. So still it is very much clear that if you are working with sodium, you can see that its last shell is having 1 electron, and in order to become stable, it can lose this 1 electron so that its octet configuration is completed. That is basically how group 1A elements they become stable. That is, they lose their electron. That means all of the members of group 1A would be losing their valence electron, and they would be forming, what do you say, mono valent cations. Now, you can also understand this term easily. Mono means one, valent charge. So charge can be either positive or negative. Cations is usually for plus. So I can write these, that is lithium, sodium, potassium, or any of the members of group 1A would lose their one valence electron to have a charge of +1. Sodium would lose valence electron to have a charge of +1. Potassium would similarly lose one valence electron to have a charge of +1. So now if you understand this concept, we can proceed to the further groups and it would be relatively far more easy. Let's consider group 2A for instance. So in group 2A, we have beryllium, magnesium, calcium, strontium, barium, and radium. So if you are working with group 2 elements, so like group 1 elements, what you can say, group 2 elements would have 2 valence electrons. That means if they want to become stable, what they can do? They can easily lose these 2 electrons. How? It's the same idea behind it. So if you are working with, let's say, magnesium, magnesium has an atomic number of 12. So its K shell would be having 2 electrons, L shell would be having 8 electrons, M would be having 2 electrons. So now you can see the last shell, it is having 2 electrons. And basically now since this is magnesium, it is having 2 electrons. So you can see it should be belonging to group 2 and that is very much the case. Magnesium is found in group 2. Then if magnesium wants to become stable, it can either lose these 2 electrons, that is one of the cases, or either it can gain 6 more electrons. Now I leave it to you whether you decide what's easy, losing 2 electrons or gaining 6 electrons. Obviously, losing 2 electrons is very easy. That means magnesium, in order to become stable, would get a charge of +2 and it would be having 2 electrons lost. So you can say this as magnesium would be a, if you name this accordingly, monovalent cation for group 1. So you can create another name for group 2 elements. There would be divalent cations. Now, similarities in group, of the properties between group 1 and 2 is something like this, that if you are working with group 1 elements or group 2 elements, one thing, they are all metals. Group 1A elements are known as alkali metals and group 2A are known as alkaline earth metals. And we would be discussing this term alkali later on in acids and bases. For now on, it's only a factual knowledge, group 1 and 2. Now, if you move down the group, in group 1, the reactivity increases. Same goes for group 2. That means lithium, if you are comparing lithium with sodium, and the idea is reactivity has to increase down the group. So lithium would be less reactive as compared to sodium, and sodium would be less reactive as compared to potassium. Put it another way, potassium would be far better reactive as compared to lithium as compared to sodium. So as we move down the group, reactivity increases. Same goes for beryllium and magnesium. If we are comparing calcium, let's say, with magnesium, so which one of these two would be more reactive? So answer is calcium would be more reactive as compared to magnesium. So this is one of the scenarios. The other scenario is, however, melting and boiling points. It is very hard to generalize the idea of melting and boiling points, but usually speaking or commonly speaking, what we can say is down the group, melting and boiling point, it increases. That needs to be understood also. See, if you are comparing lithium with sodium, so you can see easily that lithium would be having only 2 shells. However, sodium would be having 3 shells. Potassium would be having 4 shells. That is, its period number is 2, its period number is 3, its period number is 4. So lithium 2, sodium 3, potassium 4. If same amount of energies are provided to potassium, sodium and lithium, so lithium is having a very simpler structure as compared to sodium and potassium. That means lithium would melt, it may boil, it may gain energy rapidly as compared to sodium and potassium. Reason being, less number of shells or simple structure. Now, moving towards the other periods, same goes for group 3. If you are working with group 3 elements, let's say we are working with group 3 elements. Group 3 has boron, aluminium, gallium, indium, thallium. So if we are working with group 3 elements, what is the scenario? You can link it to the other groups as well. These elements, these groups would be having 3 electrons in their outermost shell. So in order to become stable, what they would be doing? They would be losing their 3 electrons. So group 3 elements would be becoming trivalent cations. Trivalent cations. Now, let's stop this here and jump to right to group 8. It is not 7, it is 8. So if you are working with group 8 elements, that is helium, neon, argon, krypton, xenon, and radon. So group 8 elements would obviously be having either 8 electrons or they would be having 2 electrons. Only helium is an exception here. It has 2 valence electrons. Remaining all the elements, they have 8 electrons. So now this violates this knowledge that, sir, when you are comparing, when you initially mentioned that this group number indicates the number of valence electrons, so helium should be having 8 electrons. So why does it have 2 electrons? And if it is having 2 electrons, then why is it not placed in group 2? So we need to consider this it is very simple to understand. See, group 8 elements, let's exclude helium from here. For one instance, let's consider helium is not here. Neon, argon, krypton, xenon, and radon are present in group 8 and they have 8 valence electrons. That means these elements don't need to react. That means they are stable. So if I bring helium into group 2A family and place it somewhere here, let's say, so that means helium has 2 valence electrons. That's okay. And that also means that helium is stable. So if helium is stable, since it only have K shell, and that K shell is having 2 electrons, so helium doesn't need to react. It neither lose or it neither gain any electron. However, group 2A elements are very reactive. So if we are considering to place helium in group 2A, that is wrong, because 2A elements, they don't have K shell, number 1, as the outermost shell. Number 2, yes, they are very reactive. They are not inert. So helium being an inert is rightly placed in group 8 elements. That is the reason they are known as inert gases, noble metals, or zero group members. Why they are known as zero group members? Because they don't have any charge on them. Okay,